Hey friends, it's good to be back with you. Today I'd like to talk to you a little bit about eigenvalues. Now, if you work with linear systems or linear models of physical objects or physical systems, you're going to run across these things a lot, so we need to know what they are. Now let's do this in 3 steps. The first thing I'd like to do is tell you a little bit about sort of the mathematical basis of them. Where do they come from? The second is I'd like to give you an important example from my own engineering career, because there have been long times in my career where I pretty much lived and died on eigenvalues, metaphorically, of course. And the third, let's make this practical. Let's go to my computer and we'll use MATLAB to calculate some eigenvalues. So let's get started. Now, the first step is realizing that when mathematicians see something enough times, they give it a name, which is what we all do. So often enough, this equation shows up. AX equals lambda IX, where A is a matrix, X is a vector, lambda is just a number, it's a constant. There's the identity matrix, and there's X again. If you want to write this out in a more formal terminology, or more formal format, I guess. Running out of room. There. That's what it would look like. That's kind of cumbersome, so I'm going to stick with this. But that's what we're talking about here, where A is an n by n matrix and X is, that's not working either, is it? Hang on. N by 1, n rows in 1 column. Okay, so there we've got it. That's what we're dealing with here. Well, where does this equation show up? It shows up all kinds of places. I saw it in my own career doing structural vibrations, but it shows up in lots and lots of places. So where did the name eigenvalue come from? I told you mathematicians name something when they see it enough times. Well, sometimes the name isn't very obvious or even really very helpful. This is just one of those cases where it isn't very obvious. Now, you can look at that word. Well, it doesn't seem like it probably started out in English, and it didn't. It started out in German or maybe Dutch, I think German. And it doesn't translate super well into English. The closest I've seen is something called a characteristic equation. Well, you got to call it something. We've decided to call it eigenvalue. That's fine. English has enough words from other languages. This is just one more. We're good to go. So we've got 2 problems with this. The first one is that, if you have n equations, you can solve for n unknowns, right? Well, let's just count here. This is n by n, so there's n equations. That was, say, 4 equations. Well, there's 4 variables there, n variables. What's that? That's another variable. There are more unknowns than there are equations in this expression. That's going to be problematic, but there's a way around it. And there's another problem that's even more insidious. Well, let's rewrite this very slightly. Okay, all I did was subtract lambda IX from both sides. Well, linear algebra is still just algebra. So let's, whoops, where's my, here it is. Messed up. There we go. It's not a very good lambda either. So let's try that again. There we go. That's much better. Okay, so finally, after a little bit of fussing around, I got this. Well, that's an n by n matrix, A minus lambda I. Lambda is just some number. So that's going to give me an n by n matrix, but I don't know what lambda is. And no matter what this is in there, if I solve this, I'm going to get x equals 0. It's not very helpful, is it? Mathematicians call this the trivial solution. Okay? Trivial solution is mathematician talk for correct without being helpful, and that's certainly what's going on here. If I'm dealing with a structural vibrations problem, maybe the kind of thing I work with a lot, X means nothing's moving. That's not vibration. So what do I do with this? Well, there is a theorem that says if a system is to have a non-trivial solution, then the determinant has to be equal to 0. So let me write this out here. I want to make sure we get this. Give me a second, I'm going to write this out. Okay, there it is. There is a theorem, well proven, it's called Cramer's theorem, that says for a non-trivial solution, that is for one where x doesn't equal 0, it equals something else, the determinant of this matrix, A minus lambda I, has to be 0. I thought that to be invertible, it had to have a determinant that's not 0. This one doesn't have an inverse. Okay? In order to solve this system, that's got to be true. Right? That's a theorem that we're going to use. This is the basis. This is what makes eigenvalues work. So this is, you'll see eigenvalues of matrix function. You'll see eigenfunctions. You'll see that a lot. Well, what would this look like? I mean, okay, when you write it out this way, that lambda, by the way, that is your eigenvalue. I'm a little stuck here. Maybe an example would help. Let's try that. So I'm going to clear my board and I'm going to write out an example for us. Okay, here's a really simple system, just a 2 by 2 matrix here that I made up. And there's the identity matrix, and you can see this is A minus lambda I. And I've got these vertical lines here, so we're going to find the determinant. And remember, the reason we're doing this is that there is a theorem that says for a system where AX equals 0, which mathematicians called a homogeneous or homogeneous system, I've heard both pronunciations, that only has a solution if that determinant equals 0. That's what's motivating what we're about to do here. So let's go ahead and just write this out. Let's just keep going. Okay, all I did now was just multiply or expand this out to get to that. So far, no problem. Now, how do you take the determinant of a 2 by 2 system? Well, it's that term times that term minus that one times that one. Okay, let's do that. So I thought I'd spare you the trouble of watching me grind all this out by hand. So let's just go over it quickly. There's the determinant still in matrix form. When you expand it all out, remember, that term times that term minus that one times that one for a 2 by 2 system, you get this. Well, expand it all out and you get this nice little quadratic equation, quadratic polynomial. Run it through the quadratic equation and you get the 2 eigenvalues right here. Now, it's pretty clear that this works fine for a 2 by 2 system. 3 by 3, it starts getting ugly. Anything after that is really not tractable by hand. Now, eigenvalues, like I said, show up everywhere, and they're almost always calculated numerically. And it's routine to calculate eigenvalues for very, very large systems. Now, I work with vibrating structures a lot. I've worked with acoustics, structural dynamics, aeroelasticity, flutter, musical instrument design, all that stuff. Something's vibrating, usually in the presence of either airflow or a static air mass. But the bottom line is, here's an equation I see absolutely all the time. Okay? I see that absolutely all the time. Alrighty, so let's see. Kx, okay, K is a stiffness matrix. That's a mass matrix. Okay. X is a deformed shape, and omega squared, which I'm going to call lambda, omega is a vibration frequency, right? So wait a minute, we just went from this generic eigenvalue thing that has these properties that I've told you were interesting, and all of a sudden, now I'm finding resonant frequencies of vibrating structures. That's about as practical as problems get. So this doesn't exactly look like the eigenvalue equation I just showed you, did it? That form was called normalized form. This is called a generalized eigenvalue problem. Well, how do you turn one of them into the other? It's easy. All I've got to do is multiply through by the inverse of the mass matrix. So I say m minus 1 k Now what's inverse of m times m. That's not a very good m. There. That's going to be the identity matrix, isn't it? So I don't know what I'll call this. I'll call this, I don't know, how about A? Oh, son of a gun, there it is. There it is. So whenever I make a finite element model of a structure, whatever it is, that finite element model includes a stiffness and a mass, and because of the way we solve it, that omega squared just naturally drops out. Just call that your eigenvalue. Do this. Now what happens when I solve this? What happens when I find lambda? Well, the square root of lambda is the frequency. Okay? There are n eigenvalues for an n by n system. So if I have a model that has 1,000 degrees of freedom, I'm going to calculate 1,000 possible resonant frequencies. Now in practice, you only generally care about the first couple. Get that out of the way here. And what does x mean if you solve that? That's called the eigenvector. And the eigenvector is the vibrating shape. So if I'm plucking a guitar string, when I say it's made up of the first 10 modes, the first 10 frequencies, well, there's 10 of these too, and there's different proportions of each of those 10 shapes that make up the vibrating shape of the string. There's one problem I've been kind of tap dancing around here. I already told you that we have n plus 1 unknowns for n equations. And I just told you we're calculating that one. So we know if there's n elements in the eigenvector, there's one of them we don't know. Well, how do you fix that? Well, when you calculate eigenvectors, you do one of a couple things. The simplest one is just arbitrarily assign one a value of 1 and then use that to figure out the others. So what that means is when you calculate an eigenvector from this and you find the vibrating shape, let's back up a second. What do I mean by vibrating shape? Well, hang on. Here's my guitar. Here's one of them. One of many, I'm afraid. Okay, if I pluck a string, that should be vibrating at the fundamental is 82.4 hertz if this thing is in tune. But that's not the only frequency present. Other frequencies are present too, right? The frequencies that are present are these, and the shapes are that. Well, what does a shape mean? Well, if I look at a string that's vibrating, and those are the ends of the string. These are the, one end is the nut and one end is the saddle on a guitar. They don't look like that, but they act like that. Well, the first vibrating shape is half a sine wave. Well, that isn't moving in time, but my guitar is. So what's up with that? Well, if I were to place a strobe light in front of the guitar and have it flash at 82.4 hertz to freeze the vibration, and it was only vibrating in that mode, I somehow managed to pluck it exactly right so there was only one frequency present, the strobe light would show it doing that. It would freeze the motion. So it's actually vibrating like this, but if you could freeze it, it would look like that. What's the second mode of a string look like? Well, it's more of a sine wave. There's a full sine wave. What's the third mode look like? Well, it's a sine wave and a half, I think. It looks like that. And it keeps going like that. So when I calculate all the eigenvalues, the resonant frequencies of that string, when I play it, those are actually the frequencies you measure when you listen to the guitar. And if you were to freeze the motion, okay, and what you'll see is a linear combination of those, a linear combination of the eigenvectors. Now, since we don't know the absolute magnitude of the eigenvector, because we had to arbitrarily just assign one of the elements in order to solve, I don't know how much of each one of those is present unless I have one more equation. What would that one more equation be? What if I knew the input force? Let me grab the guitar again. What if, instead of me just randomly plucking, I had, maybe this has a sensor or something on it. This is a guitar pick. And I know what force I'm putting in and I know where. With that extra equation of knowing what the force is, that gives me n plus 1 equations now, and I can now solve for n plus 1 unknowns, and I really do know what that is. But in order to find an absolute magnitude of that, I have to know what the input force is. All right? So with all that, let's go to MATLAB and start figuring out how to calculate eigenvalues and eigenvectors.